Hello there, and welcome to the Sleepy Library. It's lovely to have you here tonight. Before we begin our gentle journey into the invisible world around us, I'd love to know where you're listening from. Perhaps you're tucked into bed, the lights dimmed low, or maybe you're on a quiet evening walk, earbuds in, watching the streetlights flicker on one by one. Wherever you are, I hope you're comfortable, safe, and ready to let your mind wander through the fascinating yet soothing realm of science. If you enjoy these relaxing explorations of our universe, a like and subscribe really helps this channel continue sharing these peaceful moments of discovery. And to those of you already subscribed, thank you from the bottom of my heart. Your support means everything. Tonight, we're going to explore something truly remarkable. Something so fundamental to existence that you've been experiencing it every single moment of your life without even realizing it. We're going to talk about electromagnetic fields, the invisible forces that shape everything around you, from the light streaming through your window to the thoughts flowing through your mind right now. Don't worry if that sounds complex. We'll take our time, moving slowly and gently through each idea, letting the wonder of it all wash over you like a warm wave. So, settle in, take a deep breath, and let's begin our journey into the hidden architecture of reality. Imagine for a moment that you could see the invisible. Not just the air around you, but the forces that fill every cubic centimeter of space. If you had such vision, you would see something extraordinary. You would see fields, endless, shimmering fields of energy stretching in all directions, weaving through walls, flowing through your body, connecting everything to everything else. These are electromagnetic fields, and they are perhaps the most ubiquitous yet overlooked aspect of our universe. They are the stage upon which the entire play of existence unfolds, the invisible threads that connect the stars to your smartphone, the sun to your skin, and one atom to another across the vast expanses of space. To understand electromagnetic fields, we need to start with something simpler, something you've probably encountered since childhood: electric charges. You know that feeling when you rub a balloon against your hair and it stands on end, reaching toward the balloon as if pulled by invisible strings? That's electricity at work. Or, more precisely, that's an electric field revealing itself. An electric field is a region of space around a charged object where other charged objects feel a force. Think of it like the warmth radiating from a fire. You can't see the heat itself, but you can feel its effects. The closer you get, the stronger the effect. The farther away, the gentler it becomes. Now, electric charges come in two varieties, which we call positive and negative. These names are purely conventional, chosen long ago by scientists who had no idea what they were really dealing with. But the behavior is clear and consistent. Like charges repel each other. Two positive charges push apart. Two negative charges push apart. But opposite charges attract. A positive and a negative charge pull toward each other with a force that depends on how much charge they carry and how far apart they are. This simple rule, this push and pull between charges, creates the electric field. Every charged particle in the universe creates its own electric field, extending outward in all directions, weakening with distance, but never quite reaching zero. Even across the vast emptiness of space, an electron on Earth creates a tiny, infinitesimal electric field that reaches to the farthest galaxies, though its effect there would be immeasurably small. But electricity is only half the story. There's another force, equally fundamental and mysteriously connected: magnetism. You've seen magnets, of course. Perhaps you've played with them, feeling that strange push and pull, that invisible hand that seems to reach through empty space. Magnetic fields work in much the same way as electric fields. They exist in regions around magnetic objects, and they exert forces on other magnetic objects and on moving electric charges. But here's where things get interesting, where the universe reveals one of its most elegant secrets. Electricity and magnetism are not separate forces. They are two aspects of the same fundamental phenomenon. They are unified, intertwined, inseparable. And this connection was discovered in one of the most beautiful moments in the history of science. In the year 1820, a Danish physicist named Hans Christian Ørsted was giving a lecture to his students. During a demonstration, he passed an electric current through a wire near a compass. Something unexpected happened. The compass needle, which always points north, suddenly twitched and turned to point toward the wire. Ørsted had stumbled upon something profound. He had discovered that an electric current, which is simply moving electric charge, creates a magnetic field. This was revolutionary. It meant that electricity and magnetism weren't separate phenomena at all. They were connected, linked by motion. A stationary electric charge creates only an electric field. But set that charge in motion, make it flow as a current, and suddenly a magnetic field springs into existence around it, wrapping the moving charge in invisible loops of magnetic force. This discovery opened a door. If electricity could create magnetism, then perhaps the reverse was also true. Perhaps magnetism could create electricity. In 1831, Michael Faraday, working in his laboratory in London, proved exactly that. He showed that a changing magnetic field could induce an electric current in a wire. Not a steady magnetic field, mind you, but a changing one. Movement was the key. When you move a magnet near a coil of wire, or when you move a coil of wire near a magnet, the magnetic field through the coil changes, and this change creates an electric current. This principle, called electromagnetic induction, is the foundation of nearly all modern electrical technology. Every generator that produces electricity, every electric motor that converts electricity into motion, every transformer that adjusts voltage, they all work because of this deep connection between electricity and magnetism. But the true unification came from James Clerk Maxwell, a Scottish physicist with an extraordinary gift for mathematical thinking. In the 1860s, Maxwell took all the known laws of electricity and magnetism, the observations of Ørsted and Faraday and many others, and he wove them together into a single mathematical framework. 4 elegant equations, now known simply as Maxwell's equations, that described how electric and magnetic fields behave and how they create each other. These equations were beautiful. They were symmetrical, balanced, profound, and hidden within them was a prediction that Maxwell himself recognized, a prediction so startling that it would change everything. The equations suggested that a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. But if this is true, if each field can create the other, then something remarkable should be possible. Imagine disturbing an electric field, giving it a little shake. That disturbance creates a changing electric field. The changing electric field creates a magnetic field. But that magnetic field is also changing as it forms. And a changing magnetic field creates an electric field, which is changing, which creates a magnetic field, which creates an electric field, and on and on. What Maxwell realized was that this process could sustain itself. The fields could bootstrap each other, creating a self-perpetuating wave of electric and magnetic fields, rippling outward through space, each field creating the other in an endless dance. These waves, according to Maxwell's equations, would travel at a specific speed. When Maxwell calculated that speed, using only the known properties of electricity and magnetism, he got a number very close to 300,000 kilometers per second. And he recognized that number immediately. It was the speed of light. Light, Maxwell realized, was an electromagnetic wave. Those warm rays you feel on your face when you step into the sunshine, the gentle glow of a candle flame, the brilliant arc of a rainbow. All of it, every bit of light that has ever reached your eyes, is nothing more and nothing less than a traveling disturbance in the electromagnetic field, an oscillation of electric and magnetic fields rippling through space at the fastest speed anything can travel. This was a unification as profound as any in physics. Light, electricity, and magnetism were all aspects of the same underlying reality, the electromagnetic field. And this field, Maxwell's equations revealed, could support waves of many different kinds. Light was just one example. The equations predicted that electromagnetic waves could have any frequency at all, from the slowest oscillations to the fastest vibrations imaginable. And each different frequency, each different kind of electromagnetic wave would have its own character, its own way of interacting with matter. This spectrum of electromagnetic waves stretches from the extremely low frequencies, where the waves are kilometers long, all the way to the highest energies, where the waves are smaller than atoms. And we've given names to different regions of this spectrum based on how we discovered them and how they behave. At the very bottom, with the longest wavelengths and lowest frequencies, we have radio waves. These are the waves that carry your favorite music through the air to your radio, that bring television signals into your home, that allow your phone to connect to cell towers miles away. Radio waves can be enormous, stretching for kilometers from crest to crest, or they can be shorter, just a few centimeters long. They pass easily through most materials, which is why you can listen to the radio inside a building or pick up a phone call in your basement. Next up the spectrum, as the waves get shorter and the frequency increases, we find microwaves. These waves are just a few centimeters to a few millimeters long. They're perfect for heating food because water molecules happen to absorb energy at microwave frequencies, causing them to vibrate and warm up. That's how your microwave oven works. It fills the oven with electromagnetic waves at just the right frequency to make water molecules jiggle. And that jiggling, that vibration, is heat. As we continue up the spectrum, the waves get shorter still, and we enter the infrared region. Infrared waves are longer than visible light, but shorter than microwaves. You can't see them with your eyes, but you can feel them as heat. Every warm object emits infrared radiation. Your body right now is glowing with invisible infrared light, radiating away the warmth of your metabolism into the surrounding air. That's how night vision cameras work. They detect the infrared glow of warm objects, allowing us to see in the dark by converting heat into visible images. And then, in a narrow band in the middle of the electromagnetic spectrum, squeezed between the infrared below and the ultraviolet above, we find visible light. This is the only part of the electromagnetic spectrum that our eyes can detect directly. Waves with wavelengths from about 400 to 700 nanometers, oscillating hundreds of trillions of times per second. These are the waves that paint the world in color, that bring you the sight of a sunset, the green of leaves, the blue of the sky, the face of someone you love. It's remarkable, really, how narrow this visible window is. The electromagnetic spectrum stretches across more than 20 orders of magnitude in frequency, from the slowest radio waves to the fastest gamma rays. And yet, we can only see a tiny sliver of it, less than 1 octave of frequency. Evolution tuned our eyes to this particular range because our sun emits most of its energy in visible wavelengths, and because Earth's atmosphere is transparent to these frequencies. If we had evolved under a different star, or in a different chemical environment, perhaps we would see radio waves or infrared. Perhaps our whole visual experience of the world would be unrecognizably different. As we continue climbing the spectrum, just beyond violet, the highest frequency color our eyes can see, we enter the ultraviolet region. Ultraviolet light has enough energy to cause chemical changes in molecules. That's why it can tan your skin or, with too much exposure, cause painful sunburns. It's also why we can't see it. Our eyes would be damaged if ultraviolet light could penetrate to the retina. So evolution equipped the human eye with a lens that filters it out. Beyond ultraviolet, at even higher energies and shorter wavelengths, we find X-rays. These are the waves that doctors use to peer inside your body, to see your bones and organs without making a single cut. X-rays pass easily through soft tissue, but are absorbed by denser materials like bone, creating those ghostly images we've all seen. And finally, at the very top of the electromagnetic spectrum, with the shortest wavelengths and highest energies, we have gamma rays. These are the most energetic electromagnetic waves in existence, produced by nuclear processes, by the hottest and most violent events in the universe. Supernovae, black holes, the centers of galaxies, all blaze with gamma rays. Every single one of these waves, from the longest radio wave to the shortest gamma ray, is fundamentally the same thing: an oscillating electric and magnetic field rippling through space at the speed of light. The only difference is the frequency of oscillation. And yet, that simple difference in frequency creates a rainbow of phenomena, a spectrum of behaviors and interactions that fills our universe with light and color and warmth and energy. Now, you might wonder, what exactly is oscillating? When a water wave travels across the surface of a pond, we can see what's moving. It's the water itself, rising and falling as the wave passes. But electromagnetic waves can travel through the vacuum of space, through regions where there's no matter at all. So what is waving? The answer is the electromagnetic field itself. The field is the medium. In regions of space where an electromagnetic wave is passing, the strength of the electric field oscillates, growing stronger and weaker, pointing in different directions, while the magnetic field does the same, always perpendicular to the electric field and perpendicular to the direction the wave is traveling. The wave is a traveling pattern in the field itself, a disturbance that carries energy from one place to another without needing any material substance to support it. This was one of the most radical insights of 19th century physics. The electromagnetic field isn't just a mathematical convenience, a way of calculating forces between charges. It's a real physical thing. It exists in space. It carries energy and momentum. When you turn on a flashlight and aim it at a wall, electromagnetic energy flows from the bulb to the wall, traveling through the apparently empty space in between. That energy is real. You can measure it. You can feel it as warmth when the light is absorbed. The field is doing something, carrying something, even in regions where there are no charges, no matter, nothing but space and field. And here's another beautiful thing about electromagnetic waves. They always travel at the same speed in vacuum. 300,000 kilometers per second. Nothing moves faster. This speed, which we call the speed of light and denote with the letter c, is one of the fundamental constants of nature. It doesn't matter what frequency the wave has, whether it's a lazy radio wave or a ferocious gamma ray. In vacuum, they all travel at exactly the same speed. This constancy of the speed of light turned out to be crucial. It was one of the key observations that led Einstein to develop his theory of special relativity. But that's a story for another evening. For now, let's come back down to Earth and think about how these invisible fields shape our daily lives. When you wake up in the morning and flip on a light switch, you're controlling an electromagnetic field. The electricity flowing through the wires in your walls is a current of moving charges, and that current creates magnetic fields that loop around the wires. When the current reaches the bulb, it passes through a thin filament, heating it until it glows, emitting visible light, electromagnetic waves that spread out in all directions, filling your room with illumination. When you turn on your phone, you're sending commands that control the device's internal electromagnetic fields. The screen generates light by precisely controlling electric currents through millions of tiny pixels. When you make a call, your phone generates radio waves, electromagnetic signals that encode your voice and travel through the air to the nearest cell tower. That tower receives the signal, translates it, and sends it through a network of wires and more radio signals until it reaches another phone, perhaps thousands of kilometers away, where it's converted back into sound. When you stand in the sunshine, you're bathing in an electromagnetic field that originated 93 million miles away, in the roiling surface of our star. Nuclear reactions in the sun's core produce gamma rays. Those gamma rays are absorbed and re-emitted countless times, gradually losing energy, shifting to lower frequencies, working their way outward through the sun's dense interior over thousands of years. Finally, reach the surface and escape into space as visible light and infrared radiation. 8 minutes later, traveling across the vast emptiness at the speed of light, some of those waves reach Earth, pass through the atmosphere, and land on your skin. Your body absorbs the energy, feels it as warmth, uses some of it to trigger the production of vitamin D. The electromagnetic field carries that energy across space and time, connecting you directly to the nuclear furnace at the heart of our solar system. When you look in a mirror, you're seeing yourself by reflected electromagnetic waves. Light bouncing off your face hits the reflective surface, and the electrons in the metal vibrate in response, re-radiating light that travels back to your eyes. When you listen to music on wireless speakers, electromagnetic waves carry the audio signal through the air. The speakers convert those waves into vibrating diaphragms, and the diaphragms create sound waves in the air that travel to your ears. Every image you've ever seen on a screen, whether a television, a computer monitor, or your phone, exists because of precisely controlled electromagnetic fields. LED screens use semiconductors to generate light at specific wavelengths and intensities. Liquid crystal displays manipulate polarized light using electric fields. Even old cathode ray tubes used magnetic fields to steer beams of electrons that painted images on a fluorescent screen line by line. The medical world is deeply intertwined with electromagnetic fields. X-ray machines use high-energy electromagnetic waves to create images of bones and soft tissue. MRI scanners use powerful magnetic fields and radio waves to probe the magnetic properties of hydrogen atoms in your body, building up detailed three-dimensional maps of internal organs. Radiation therapy uses carefully focused X-rays or gamma rays to target and destroy cancer cells. Electromagnetic fields in the form of transcutaneous electrical nerve stimulation can provide pain relief by delivering gentle electric pulses to stimulate nerves and muscles. In the kitchen, electromagnetic fields help cook your food. Electric stoves use the heating effect of current flowing through resistive elements. Induction cooktops generate oscillating magnetic fields that induce electrical currents in metal pots and pans, heating them directly without heating the stovetop itself. Microwave ovens, as we mentioned, use electromagnetic waves at a frequency specifically chosen to make water molecules rotate rapidly, generating heat throughout the food. Transportation relies on electromagnetic fields. Electric motors, which power everything from trains to electric cars to industrial machinery, work by using magnetic fields to exert forces on current-carrying wires, converting electrical energy into motion. Magnetic levitation trains float above their tracks, held aloft by powerful electromagnets that create repulsive forces, allowing the trains to glide at high speeds. Minimal friction. Even the invisible infrastructure that surrounds us hums with electromagnetic activity. Power lines carry alternating current, and the oscillating current creates oscillating magnetic fields that extend for some distance around the wires. Radio and television broadcast towers beam electromagnetic waves across entire regions, filling the air with signals that our devices can pluck out of the electromagnetic background and decode. Wi-Fi routers create a bubble of radio waves that carry data packets encoding web pages, videos, and messages. GPS satellites orbit the Earth, continuously broadcasting precise timing signals as electromagnetic waves. Your phone receives those signals from multiple satellites, calculates how long each one took to arrive, and uses that information to triangulate your position on the surface of the planet. It's all electromagnetic fields, invisible, intangible, yet absolutely fundamental to modern life. But electromagnetic fields aren't just a human invention. They existed long before we discovered them, and they shape the natural world in countless ways. Earth itself has a magnetic field, generated by the churning motion of molten iron in the planet's outer core. This geomagnetic field extends far out into space, creating a protective bubble called the magnetosphere that shields us from the worst of the solar wind, a stream of charged particles constantly flowing outward from the sun. When particularly strong bursts of solar wind hit the magnetosphere, they can disturb Earth's magnetic field and funnel charged particles down toward the poles along magnetic field lines. These particles collide with atoms and molecules in the upper atmosphere, transferring energy and causing the air to glow with beautiful, ethereal colors. We call this phenomenon the aurora, the northern lights in the Arctic regions and the southern lights in Antarctica. Curtains and ribbons of green, red, and purple light that shimmer and dance across the night sky. A visible manifestation of the interaction between the sun's electromagnetic emissions and Earth's magnetic field. Birds, sea turtles, and many other animals can sense Earth's magnetic field and use it for navigation during long migrations. They have specialized cells containing magnetic crystals or chemical reactions that are sensitive to magnetic fields, giving them an internal compass that helps them find their way across thousands of miles of open ocean or trackless wilderness. Even some bacteria orient themselves using Earth's magnetic field, growing tiny chains of magnetite crystals inside their cells that act like compass needles. Plants respond to light, which is to say, they respond to electromagnetic waves in the visible spectrum. Chlorophyll molecules in leaves absorb red and blue light, using the energy to drive photosynthesis, the process that converts carbon dioxide and water into sugars and oxygen. The green color of plants comes from the fact that chlorophyll reflects green light rather than absorbing it. Different wavelengths of light affect plant growth in different ways, a phenomenon called photomorphogenesis. Red light promotes flowering and fruiting. Blue light encourages compact, bushy growth. Far red light triggers shade avoidance responses. Your own body is suffused with electromagnetic fields. Your nervous system operates using electrical signals. When a neuron fires, sending a signal down its length, it does so by allowing charged ions to flow across its membrane, creating a traveling wave of electrical activity. This electrical impulse, called an action potential, propagates along the nerve fiber at speeds of up to 100 meters per second. When it reaches the end of the neuron, it triggers the release of chemical messengers that cross the gap to the next neuron, where they may trigger another electrical signal. Your brain, right now, as you listen to these words, is alive with patterns of electrical activity. Billions of neurons firing in coordinated rhythms, creating complex electromagnetic fields that fill your skull. These fields are weak, but they're detectable. Electroencephalogram machines can measure them from outside your scalp, revealing patterns associated with different states of consciousness, different types of thinking, sleep, and dreaming. Your heart beats because of electrical signals. Specialized cardiac cells generate rhythmic electrical pulses that spread through the heart muscle, coordinating the contraction of different chambers in the precise sequence needed to pump blood efficiently. Electrocardiogram machines detect these electrical signals by measuring tiny voltage differences on the surface of your skin, allowing doctors to monitor the health and rhythm of your heart. Even individual cells in your body maintain electrical potential differences across their membranes, with the inside typically negative relative to the outside. This electrochemical gradient is essential for many cellular processes, from nutrient transport to signal transduction. Life itself, at the cellular level, depends on the careful control of electrical charges and electromagnetic fields. At the atomic level, everything around you is held together by electromagnetic forces. The atoms that make up your body, the chair you're sitting on, the air you breathe, they're all collections of electrically charged particles, protons with positive charge and electrons with negative charge, bound together by the electromagnetic force. The structure of atoms, the way electrons arrange themselves in shells and orbitals around the nucleus, is entirely determined by the electromagnetic interactions between the negatively charged electrons and the positively charged nucleus. When atoms bond together to form molecules, they do so by sharing or transferring electrons, creating electromagnetic attractions that hold the atoms in specific geometric arrangements. Every chemical reaction is fundamentally a rearrangement of electrons, guided by electromagnetic forces. The properties of materials, their hardness or softness, their transparency or opacity, their color, their conductivity, all arise from the behavior of electrons in electromagnetic fields. Metals conduct electricity because their electrons are loosely bound and can flow freely through the material. Insulators don't conduct because their electrons are tightly held to their atoms. Transparent materials allow light to pass through because the electrons in their atoms don't absorb visible wavelengths. Colored materials absorb some wavelengths and reflect others, and the reflected light is what we perceive as color. The strength of materials comes from electromagnetic bonds between atoms. When you push on a solid object, you're really experiencing the electromagnetic repulsion between the electrons in your hand and the electrons in the object. The solidity of matter is electromagnetic. Even though atoms are mostly empty space, with the nucleus occupying only a tiny fraction of the atomic volume, you can't push your hand through a wall because the electromagnetic fields of the electrons repel each other with enormous force at close range. Light interacts with matter through electromagnetic fields. When light enters a material, the oscillating electric field of the light wave causes the electrons in the material to oscillate in response. These oscillating electrons absorb energy from the light and then re-radiate it, often at a slightly different frequency or in a slightly different direction. This is how light can be absorbed, reflected, refracted, and scattered by matter. It's all electromagnetic interaction, the dance between the fields of the light and the fields of the electrons in the material. The colors of the sunset are electromagnetic phenomena. As sunlight passes through Earth's atmosphere, it encounters countless air molecules. The electromagnetic field of the light waves causes the electrons in these molecules to oscillate and re-radiate light. Higher frequency light, toward the blue end of the spectrum, is scattered more strongly than lower frequency light. This is why the sky appears blue during the day. You're seeing sunlight that has been scattered by the atmosphere, and blue light is scattered more than other colors. At sunset, the sun is low on the horizon, and its light must pass through a much thicker layer of atmosphere to reach your eyes. Most of the blue light is scattered away before it gets to you, leaving the redder wavelengths to dominate. That's why sunsets glow with warm reds, oranges, and pinks. It's all electromagnetic waves being scattered by the electromagnetic fields of air molecules. The stars you see at night are electromagnetic beacons. Each one is a distant sun, a massive ball of plasma held together by gravity, with nuclear reactions in its core, converting hydrogen into helium and releasing enormous amounts of energy. That energy works its way outward, eventually being radiated into space as light, as electromagnetic waves. Those waves travel across the light years, through the vast empty spaces between the stars, until a few of them happen to reach Earth and enter your eye. The light from some stars has been traveling for decades, for centuries, even for thousands of years. When you look up at the night sky, you're seeing history. You're receiving electromagnetic messages that left their sources long ago, carrying information about distant suns across the cosmos. Astronomers use electromagnetic radiation to study the universe. They build telescopes to collect light at different wavelengths, from radio waves to gamma rays. By analyzing the electromagnetic signals from distant objects, they can determine what those objects are made of, how hot they are, how fast they're moving, whether they're orbiting each other, and how far away they are. Almost everything we know about the universe beyond our own planet, we learned by studying electromagnetic waves. There's something profound in this, something almost spiritual. You are made of atoms. Those atoms are held together by electromagnetic forces. The signals traveling through your nervous system are electromagnetic. The light entering your eyes is electromagnetic. The warmth you feel from a fire or from the sun is electromagnetic. The bonds that hold molecules together, the colors you see, the sounds you hear when your ears detect pressure waves that were created by vibrating objects pushed by electromagnetic forces in speakers. Nearly every aspect of your sensory experience and your physical existence is shaped by electromagnetic fields. You are immersed in them, composed by them, connected through them to everything else in the universe. It's easy to think of yourself as separate, as an individual entity moving through empty space. But the electromagnetic field doesn't recognize those boundaries. It extends everywhere, connects everything. The field that surrounds you right now, at this very moment, overlaps with the fields of every other person on Earth, every creature, every object. We're all embedded in the same vast electromagnetic field that permeates the cosmos. When you turn on a light, the electromagnetic disturbance you create propagates outward at the speed of light. 8 minutes and 20 seconds later, that disturbance, now incredibly faint, reaches the surface of the Sun. After another few hours, it reaches the outer planets. In 4 years, it passes Alpha Centauri. The disturbance spreads and fades, but it never truly stops. In principle, the light you switched on tonight will continue expanding outward forever. A tiny ripple in the electromagnetic field, carrying infinitesimal energy to the farthest reaches of the universe. There's something wonderfully democratic about electromagnetic fields. They obey the same laws everywhere. The electromagnetic force that binds an electron to a proton in a hydrogen atom in your body is the same force that binds hydrogen atoms in a star at the far edge of the observable universe. The light that reveals the world to you operates by the same principles as the light that illuminated the lives of people 10,000 years ago, and the light that will illuminate the lives of people 10,000 years in the future. The equations Maxwell wrote down in the 1860s describe electromagnetic phenomena just as accurately today as they did then, and they'll continue to do so for as long as physics makes sense. This universality is one of the great triumphs of science. It reveals that beneath the surface complexity and diversity of the world, there are simple, elegant patterns, mathematical structures that remain constant. The universe runs on rules, and electromagnetic fields are one of those rules, woven into the very fabric of reality. And yet, for all this understanding, there's still mystery. We can describe with exquisite precision how electromagnetic fields behave, how they evolve in time, how they interact with matter. We can predict the outcome of electromagnetic experiments with stunning accuracy. But when we try to ask deeper questions, what is an electromagnetic field really? What is it made of? We find ourselves on shakier ground. In modern physics, the electromagnetic field is understood as a quantum field, a more abstract and subtle concept than the classical fields that Maxwell studied. In quantum field theory, the electromagnetic field is not simply a continuous medium. It has a grainy, discrete quality. The field can only exchange energy in specific lumps called photons. When you see light, your eye is absorbing individual photons, discrete packets of electromagnetic energy. But between emission and absorption, the photon is not quite a particle and not quite a wave. It's something stranger, a quantum of the electromagnetic field, existing in a state of potential until an interaction forces it to manifest in a particular way. This quantum nature of the electromagnetic field leads to some of the weirdest and most fascinating phenomena in physics. Vacuum fluctuations, where particle-antiparticle pairs spontaneously appear and disappear in empty space. Quantum entanglement, where measurements on one photon can instantaneously affect the state of another photon, even if they're separated by vast distances. The uncertainty principle, which says you can never know both the electric and magnetic field values at a point with perfect precision. The deeper physicists probe, the stranger the electromagnetic field becomes, revealing layers of complexity and beauty that Maxwell could never have imagined. But tonight, we don't need to venture too far into those quantum mysteries. Let's simply appreciate the classical electromagnetic field, the waves and forces that shape our everyday experience. Let's marvel at the fact that something so invisible can be so essential, so pervasive, so powerful. Think about what your life would be like without electromagnetic fields. There would be no light, because light is electromagnetic. There would be no chemistry, because chemical bonds are electromagnetic. There would be no solid matter in the way we understand it, because the structure of atoms and the forces that hold materials together are electromagnetic. There would be no you, because your body is made of atoms held together by electromagnetic forces, and your nervous system operates using electromagnetic signals. In a very real sense, without electromagnetic fields, there would be nothing at all as we know it. The electromagnetic field is not optional. It's not an add-on or an accessory to reality. It's a fundamental part of what reality is. And here's another thought to drift with as you settle deeper into relaxation. The electromagnetic waves that enter your eyes and allow you to see this world, those waves were created by events outside of you, by the sun, or by a light bulb, or by a screen. They traveled through space, carrying information, encoding the patterns of light and dark, color and form that make up visual experience. When they reached your eye, they were absorbed by molecules in your retina, triggering a cascade of electrochemical events that eventually resulted in electrical signals traveling along your optic nerve to your brain. And somehow, miraculously, those electrical signals, those patterns of electromagnetic activity in the neurons of your visual cortex, became the experience of seeing. You don't just detect light, you experience it. You perceive colors, shapes, motion, depth. You recognize faces, read words, appreciate beauty. All of this rich inner world of visual experience, arises from electromagnetic fields interacting with the matter of your brain. It's one of the great mysteries. How does electromagnetic activity in neurons give rise to conscious experience? We don't know. We can trace the pathways, measure the signals, identify the brain regions involved. But the hard problem of consciousness, the question of how physical processes become subjective experience, remains unsolved. And perhaps that's okay. Perhaps some mysteries are meant to remain mysterious, at least for now. Perhaps the wonder of it, the sheer improbability and beauty of it, is enough. You are a pattern of electromagnetic activity, temporarily organized, miraculously self-aware, capable of contemplating the very fields that give you existence. As we near the end of our journey tonight, let's take a moment to appreciate the history of electromagnetic discovery. For most of human history, people had no idea that electromagnetic fields existed. They saw lightning and wondered if it was the anger of gods. They noticed lodestones, naturally magnetized rocks that could attract iron, and thought it was magic. They knew that rubbing amber could make it attract small objects, and they called it an interesting curiosity. It took thousands of years to even begin to understand what was really happening. It was only in the 18th and 19th centuries that scientists started to systematically investigate electrical and magnetic phenomena, to measure forces, to look for patterns, to build theories. People like Benjamin Franklin, who flew a kite in a thunderstorm and showed that lightning was electricity. Alessandro Volta, who invented the battery and provided the first reliable source of electric current. Hans Christian Ørsted, who discovered the connection between electricity and magnetism. Michael Faraday, who visualized fields and discovered electromagnetic induction. André-Marie Ampère, who studied the magnetic forces between current-carrying wires. James Clerk Maxwell, who unified it all into a single mathematical theory. Each of these scientists was exploring the unknown, following curiosity, trying to understand forces they couldn't see. They had no idea their work would lead to the technological civilization we live in today. Maxwell didn't write his equations thinking about smartphones or GPS satellites or MRI machines. He was trying to understand nature, to find the patterns, to see the deeper order. And yet, his equations, these abstract mathematical relationships, turned out to describe something so fundamental that they enabled the entire modern world. This is the power of basic science, of curiosity-driven research. You never know where it will lead. You study magnetism because it's interesting, and a century later, your descendants are communicating across continents using radio waves. You investigate the way metals respond to light, and a few generations later, people are using that knowledge to build solar panels and light-emitting diodes. The practical applications follow from the understanding, but the understanding comes first, born from wonder and careful attention to the natural world. And that brings us full circle to where we started, to the invisible fields that surround you right now. As you lie there, breathing slowly, feeling your body relax, know that you're cradled in a web of electromagnetic interactions. The atoms in your body are humming with electromagnetic energy. Your heart beats with electrical rhythms. Your brain dreams in patterns of electrical activity. The device you're using to listen to this video is controlling electromagnetic fields to produce sound. If you're lying in a dark room, infrared radiation is gently radiating from your warm skin into the cooler air. If there's any light at all, those electromagnetic waves are bouncing around, reflecting off surfaces, painting the world in photons. The Earth's magnetic field extends through your location, a vast, gentle presence that's been there for millions of years, holding off the solar wind, creating auroras, guiding migrating birds. And beyond that, the electromagnetic radiation from the sun, from distant stars, from galaxies billions of light years away, is passing through you right now, a ceaseless rain of photons carrying messages from across the universe. You are not separate from any of this. You are part of it. You are an electromagnetic phenomenon, a pattern in the field, temporarily coherent, gloriously complex, peacefully existing in this moment. So, as we close, let's rest in this knowledge. The hidden forces that shape everything are not really hidden at all. They're right here, right now, in every moment, in every interaction. They're the light that lets you see, the warmth that keeps you comfortable, the signals that connect you to others, the bonds that hold your body together. They're the fields that make existence possible, that weave the cosmos into a connected whole. You've been living in this sea of electromagnetic fields your entire life. Now you know it's there. Now you can feel it, not with your hands, but with your mind. You can sense the profound beauty of it, the elegant simplicity underneath the complexity, the way everything fits together into a grand, unified pattern. The universe is not a collection of separate things happening randomly. It's a symphony of fields and particles, all influencing each other, all connected by forces that extend across space and time. And you are part of that symphony. Your atoms sing the same song as the atoms in stars. The light in your eyes is the same light that left distant galaxies millions of years ago. The electromagnetic fields in your nervous system are built from the same fundamental principles that govern the behavior of fields everywhere in the cosmos. There's a certain peace in that realization, a sense of belonging. You are home. You've always been home. You're not a stranger in a cold, uncaring universe. You're woven into it, made from it, connected to it in ways both seen and unseen. The electromagnetic fields that shape everything also shape you. They are the invisible threads that tie your existence to the existence of everything else. And maybe, just maybe, understanding that can help you rest a little easier, can help you feel a little less alone, can help you appreciate the miracle of this moment, this breath, this consciousness, this beautiful, temporary pattern of electromagnetic activity that is you, experiencing itself, wondering about itself, peacefully present in the eternal now. Now, let's wander into another beautiful aspect of electromagnetic fields, something that connects the very large to the very small, the cosmic to the personal. The electromagnetic force is one of the four fundamental forces of nature. Alongside gravity, the strong nuclear force, and the weak nuclear force, electromagnetism shapes the structure of reality at every scale. But here's something remarkable. Of these four forces, electromagnetism is the only one you directly experience in your everyday life, aside from gravity. The strong force binds quarks together inside protons and neutrons, operating at distances smaller than an atomic nucleus. The weak force governs certain types of radioactive processes, also at subatomic scales. Gravity pulls you toward Earth and holds the planets in orbit around the Sun. But nearly everything else you experience, every sensation, every interaction with matter, every photon that enters your eye, is electromagnetic. When you touch something, when you feel the texture of fabric or the coolness of metal, you're not actually making contact in the way you might imagine. The atoms in your fingers never actually touch the atoms in the object. What you feel is electromagnetic repulsion, the force between the electrons in your skin and the electrons in the surface you're touching. They push against each other, and your nervous system interprets that push as the sensation of touch. The same is true when you sit in a chair or stand on the ground. You're floating, ever so slightly, on a cushion of electromagnetic force. The atoms in your body and the atoms in the chair are keeping each other at bay through their electric fields. This repulsion is so strong, so absolute, that matter almost never overlaps with other matter. You can push and push against a wall, exerting tremendous force, and you'll never push through. The electromagnetic repulsion will always win. Unless you apply such extreme pressure that you break the chemical bonds holding the material together. Think about what this means. The solidity of the world, the resistance you feel when you lean against a tree or pick up a stone, is not the result of matter being fundamentally solid. It's the result of electromagnetic forces creating an illusion of solidity. At the level of atoms, everything is mostly empty space. If an atom was scaled up to the size of a football stadium, the nucleus would be a small marble at the center, and the electrons would be tiny specks orbiting somewhere in the upper seats. Everything in between is empty, just space and fields. And yet, when trillions upon trillions of atoms organize themselves into a rock, the combined effect of their electromagnetic fields makes that rock feel completely solid, impenetrable, dense. The illusion is perfect. You would never guess, just from touching it, that it's almost entirely made of nothingness, held together by invisible forces. This is one of the most counterintuitive truths of physics. Matter is not matter in the way we think of it. It's energy and fields, organized in specific patterns, creating stable configurations that persist over time. And all of it, every bit of structure, is held together by the electromagnetic force. Let's think about energy for a moment. Because electromagnetic fields are also about energy, about the way energy moves through space and transforms from one form to another. When sunlight warms your face, energy that was created by nuclear fusion in the sun's core is being transferred to your skin across 93 million miles of empty space. That energy travels as electromagnetic waves, as photons, moving at the speed of light. When those photons strike your skin, they're absorbed by molecules in your cells. The energy of the photon causes the molecule to vibrate more vigorously, which we perceive as heat. The electromagnetic field carried that energy across the vast gulf of space, preserved it perfectly during the 8-minute journey, and delivered it precisely to your skin. This is one of the most amazing things about electromagnetic waves. They can transport energy over arbitrary distances without losing information or degrading significantly, as long as nothing absorbs them along the way. A photon that left a distant galaxy billions of years ago, traveling through the expanding universe, through clouds of gas and dust, can arrive at a telescope on Earth with its energy and information intact. Astronomers can capture that photon, analyze its wavelength, and learn about conditions in that galaxy billions of years in the past. The electromagnetic field is a carrier of information across both space and time. This property makes electromagnetic radiation incredibly useful for communication. Every radio signal, every television broadcast, every Wi-Fi packet, every cell phone call works by encoding information into electromagnetic waves and sending those waves through the air or through space. The waves travel at the speed of light until they reach a receiver, which decodes the information and presents it to a human user. In a very real sense, the modern world runs on electromagnetic fields. The entire global communication network, all the satellites, all the fiber optic cables carrying laser light, all the radio towers and cell towers and broadcast stations. They're all systems for generating, transmitting, and receiving electromagnetic waves at carefully controlled frequencies and with precisely encoded information. Without electromagnetic fields, there would be no internet, no television, no radio, no GPS, no remote controls, no wireless anything. We would be isolated, unable to communicate beyond the range of our voices or the distance a physical message could be carried. But electromagnetic fields don't just carry energy and information. They also exert forces, and those forces can do work. An electric motor is a beautiful example of this principle in action. Pass an electric current through a coil of wire in the presence of a magnetic field, and the magnetic field exerts a force on the current-carrying wire, causing the coil to rotate. Connect that rotating coil to an axle, and you have a motor that converts electrical energy into mechanical motion. This simple principle, discovered in the early 19th century, transformed civilization. Before electric motors, mechanical power came from human or animal muscle, from water wheels and windmills, from steam engines burning coal or wood. These power sources were difficult to control, inefficient, often dangerous, and tied to specific locations. You couldn't move a waterfall or a coal-burning boiler easily. But electric motors changed everything. With electric motors, power could be generated at centralized plants and distributed through wires to homes, factories, and businesses. Motors could be made in any size, from tiny mechanisms in wristwatches to massive machines driving factory equipment. They were clean, quiet, efficient, and easily controlled. The widespread adoption of electric motors in the 20th century enabled modern industry, modern transportation, modern life as we know it. And all of it is based on the electromagnetic force. The reverse process is equally important. If you take a coil of wire and rotate it in a magnetic field, the changing magnetic field through the coil induces an electric current in the wire. This is the principle behind electric generators. Spin a magnet near a coil, or spin a coil near a magnet, and you generate electricity. Most of the electricity used in the world today is produced this way. In power plants, whether they burn coal, natural gas, or use nuclear reactions, the heat produced is used to create steam. The steam drives a turbine, a wheel with blades that spin when pushed by the steam. The turbine is connected to a generator, a device containing coils of wire that rotate in a strong magnetic field. As the coils spin, electromagnetic induction creates electric current, which flows out through transmission lines to the electrical grid. Hydroelectric dams use falling water to spin turbines. Wind farms use wind to spin turbines. In every case, the mechanical energy of rotation is converted into electrical energy through electromagnetic induction. This elegant symmetry, where electric currents create magnetic fields and changing magnetic fields create electric currents, is one of the most profound discoveries in all of physics. It means that electricity and magnetism are not just related, they are two aspects of the same phenomenon, two sides of the same coin. You can convert one into the other, back and forth, with perfect efficiency, in principle, limited only by practical considerations like resistance and friction. And this convertibility has made modern technology possible. Every transformer that adjusts voltage levels, every motor, every generator, every induction cooktop, every wireless charging pad, they all exploit this beautiful interplay between electricity and magnetism. The electromagnetic field is not passive. It's active, dynamic, responsive. It can push and pull on charges, induce currents, carry energy, store information, transform one form of energy into another. It's the most versatile of all the fundamental forces, and it's the one we've learned to control most precisely. There's something deeply satisfying about understanding these connections, about seeing how a handful of basic principles, discovered painstakingly over centuries, can explain such an enormous range of phenomena. The same equations that describe a compass needle aligning with Earth's magnetic field also describe how your microwave oven heats food, how your phone receives signals, how stars emit light, how atoms hold together. The universe is not a collection of unrelated mysteries. It's a coherent whole, governed by consistent principles that apply everywhere and everywhen. And the electromagnetic field is one of those principles, woven into the very fabric of existence. You don't need to understand all the mathematics to appreciate the beauty of this. You don't need to be able to solve Maxwell's equations to feel a sense of wonder at the realization that light, electricity, and magnetism are all the same thing, viewed from different angles. Just knowing that these connections exist, that the world has this deep underlying order, can change the way you see reality. It can make the ordinary seem miraculous. A light bulb isn't just a device that produces light. It's a technology that converts the motion of electrons into electromagnetic waves that your eyes can detect. A radio isn't just a box that plays music. It's a receiver that plucks specific frequencies out of the electromagnetic chaos filling the air and decodes them into sound. Let's talk for a moment about one of the stranger aspects of electromagnetic fields, something that brings us to the edge of our everyday intuition. Electromagnetic fields can exist in a vacuum, in completely empty space, with no matter present at all. This was a radical idea when it was first proposed. In the 19th century, scientists believed that waves needed a medium to propagate through. Water waves need water. Sound waves need air or some other material. So, when light was shown to be a wave, scientists assumed there must be some medium filling all of space, some invisible substance through which light waves traveled. They called this hypothetical substance the luminiferous ether. The ether was supposed to be everywhere, permeating all of space, yet somehow invisible and without mass, offering no resistance to the motion of planets and stars. It was a strange concept, and, as experimental techniques improved, physicists tried to detect the ether, to measure Earth's motion through it. The most famous of these experiments was performed by Albert Michelson and Edward Morley in 1887. They used an interferometer, an extremely sensitive device that could detect tiny changes in the speed of light, to look for differences in light speed depending on Earth's direction of motion through the supposed ether. If the ether existed, light should travel slightly faster or slower, depending on whether it was moving with or against Earth's motion through the ether. But Michelson and Morley found nothing. No matter which direction they pointed their apparatus, the speed of light was always the same. It was a null result, and it was profoundly puzzling. The solution to this puzzle came from Einstein in 1905, with his theory of special relativity. Einstein realized that the speed of light is a fundamental constant, the same for all observers, regardless of their motion. There is no ether. Light doesn't need a medium to propagate through. The electromagnetic field is the medium. It exists in its own right, as a fundamental aspect of reality, not as a disturbance in something else. Space itself, even when completely empty, can support electromagnetic fields. Those fields can oscillate, creating waves that propagate at a fixed speed, the speed of light. This was a profound shift in thinking. It meant that space wasn't just a passive stage on which events occur. Space has properties. It can carry fields, support waves, store energy. The vacuum isn't empty in the way we usually think of emptiness. It's full of potential, full of fields at their lowest energy state, ready to spring into action if disturbed. In quantum physics, this idea becomes even stranger. The vacuum is not truly empty. It's seething with quantum fluctuations, virtual particles and antiparticles popping into existence for brief moments and then vanishing again. These fluctuations are real. They have measurable effects. They cause tiny shifts in the energy levels of atoms, effects that have been detected with extraordinary precision. The vacuum, it turns out, is an active, dynamic thing, not a passive void. This connects to another beautiful idea, the idea that all of reality can be understood as fields. Not just the electromagnetic field, but other fields too. There's an electron field, a quark field, a neutrino field, a Higgs field, and so on. Each type of particle is an excitation of its corresponding field, a ripple or a vibration in that field. When we say an electron is at a particular location, we mean that the electron field at that location has a certain amplitude and is in an excited state. This perspective, called quantum field theory, is the foundation of modern particle physics. It describes all known particles and forces, except gravity, with remarkable accuracy. And at the heart of this theory, one of the oldest and most thoroughly tested quantum field theories is quantum electrodynamics, the quantum theory of the electromagnetic field. In quantum electrodynamics, photons are excitations of the electromagnetic field. When an atom emits light, the electromagnetic field transitions from one state to another, creating a photon. When that photon is absorbed by another atom, the electromagnetic field transitions again, and the photon ceases to exist. The photon isn't a little ball of light traveling through space. It's a quantum of the field, a discrete amount of energy and momentum carried by a traveling disturbance in the electromagnetic field. This quantum nature of the electromagnetic field has profound consequences. It means that electromagnetic interactions between charged particles are mediated by the exchange of photons. When two electrons repel each other, they do so by exchanging virtual photons, photons that exist only briefly, long enough to carry momentum from one electron to the other. This is a very different picture from the classical idea of an electric field extending through space. But both pictures are useful. In situations where the fields are strong and involve many photons, the classical picture works perfectly well. But in situations where individual photons matter, where you're detecting light one photon at a time, you need the quantum picture. The The two descriptions are complementary, different ways of thinking about the same underlying reality. And what is that underlying reality? It's the electromagnetic field, behaving sometimes like a continuous wave, sometimes like a stream of particles, depending on how you interact with it and how you measure it. This duality, this wave-particle complementarity, is one of the central mysteries of quantum mechanics. It's not that light is sometimes a wave and sometimes a particle. It's that light is something richer than either concept, something that exhibits wave-like properties in some situations and particle-like properties in others, but is fundamentally neither and both. Let's take a moment to appreciate the historical journey that led to our current understanding of electromagnetic fields. It's a story of incremental discovery, of patient observation, of brilliant insights and occasional blind alleys. It spans centuries and involves dozens of scientists from different countries, different eras, different cultures, all building on each other's work. The ancient Greeks knew about static electricity and magnetism. They noticed that amber, when rubbed, could attract light objects. They knew that lodestones, certain rocks, could attract iron. But they had no theory to explain these phenomena, no concept of fields or forces in the modern sense. For thousands of years, these observations remained curiosities, interesting but not understood. It wasn't until the 18th century that scientists began systematic investigations. Benjamin Franklin, in the American colonies, experimented with electricity, showing that lightning was an electrical phenomenon, establishing the convention of positive and negative charge. In Europe, Charles Coulomb measured the force between charged objects and between magnetic poles, discovering that the force decreased with the square of the distance. This was the first hint of the mathematical structure underlying electromagnetism. In the early 19th century, the pace of discovery accelerated. Alessandro Volta invented the battery, providing a steady source of electric current for experiments. Hans Christian Ørsted discovered that electric currents create magnetic fields. André-Marie Ampère investigated the forces between current-carrying wires, laying the groundwork for electromagnetism. Michael Faraday, working in London, made some of the most important discoveries. He introduced the concept of field lines, imagining space filled with lines of force emanating from charges and magnets. He discovered electromagnetic induction, showing that changing magnetic fields create electric currents. He showed that electricity, magnetism, and light were all related phenomena. Faraday was not particularly mathematical, but he had an extraordinary physical intuition, a gift for visualizing invisible forces and imagining how they behaved. His ideas, expressed in everyday language and illustrated with careful experiments, provided the foundation for the next great step. That step was taken by James Clerk Maxwell, a Scottish physicist with formidable mathematical skills. Maxwell took Faraday's ideas about fields and electric and magnetic forces and expressed them in the language of mathematics. He wrote down 4 equations, now known as Maxwell's equations, that completely described all electromagnetic phenomena known at the time. More than that, Maxwell's equations predicted the existence of electromagnetic waves traveling at the speed of light, and Maxwell realized that light itself must be an electromagnetic wave. This was one of the great unifications in physics, comparable to Newton's unification of terrestrial and celestial mechanics. Light, electricity, and magnetism, which had seemed like separate phenomena, were revealed to be aspects of a single thing, the electromagnetic field. Maxwell's equations showed how to calculate the behavior of this field in any situation. They were elegant, symmetrical, profound, and they worked. They predicted new phenomena that were later confirmed experimentally, but Maxwell didn't live to see many of these confirmations. He passed away in 1879 at the age of 48. It was left to Heinrich Hertz, a German physicist, to experimentally verify Maxwell's predictions. In 1886, Hertz built apparatus to generate and detect electromagnetic waves at radio frequencies. He showed that these waves behaved exactly as Maxwell had predicted, traveling at the speed of light, reflecting, refracting, and interfering like any other wave. Hertz had discovered radio waves, though he didn't realize their practical importance at the time. Within a few decades, Guglielmo Marconi and others would develop radio communication, using electromagnetic waves to send messages across vast distances. The age of wireless communication had begun. In the early 20th century, the understanding of electromagnetic fields deepened further with the development of quantum mechanics and special relativity. Einstein's theory of special relativity showed that electric and magnetic fields are not separate entities, but different aspects of a single electromagnetic field, viewed from different reference frames. An electric field in one reference frame becomes a combination of electric and magnetic fields in another frame, moving relative to the first. This meant that electricity and magnetism were even more deeply unified than Maxwell had realized. They were relativistic partners, intrinsically connected by the structure of space-time itself. Then came the quantum revolution. Max Planck, Einstein, Niels Bohr, and others showed that light comes in discrete packets, photons, and that the electromagnetic field itself has a quantum nature. This led to the development of quantum electrodynamics, a theory that describes the quantum behavior of electromagnetic fields and their interaction with charged particles. Quantum electrodynamics was developed primarily in the 1940s and 50s by Richard Feynman, Julian Schwinger, and Shinichiro Tominaga, who shared the Nobel Prize for their work. It's one of the most successful theories in all of science, making predictions that have been confirmed to extraordinary precision, sometimes to better than 1 part in a billion. This long historical arc, from the ancient Greeks noticing that amber could attract feathers, to modern physicists calculating the behavior of photons to 10 decimal places, is a testament to the power of curiosity, patience, and reason. Each generation of scientists built on the work of previous generations, refining ideas, correcting mistakes, extending theories to new domains. The process was messy, non-linear, full of false starts and passionate debates. But over time, a coherent picture emerged, a deep understanding of how electromagnetic fields work, and that understanding has transformed human civilization. It's given us electric lighting, radio, television, computers, the internet, medical imaging, wireless communication, and countless other technologies that define modern life. It's also given us a sense of connection to the cosmos, a realization that the same fields that power our devices also fill the space between stars, carrying light from the farthest reaches of the universe to our telescopes and our eyes. Let's return in these closing thoughts to something more personal, more immediate. You are lying there, or sitting there, or walking there, somewhere in the world, experiencing this moment. The air around you is filled with electromagnetic waves, from radio stations and cell towers, from Wi-Fi routers and satellites, from the screens of nearby devices. Most of these waves pass right through your body without you noticing. They're too low in energy to interact significantly with your cells. They're part of the invisible electromagnetic environment, the sea of radiation we all swim in. But some electromagnetic waves matter very much to you. The visible light in your environment, if there is any, is constantly entering your eyes, providing the visual information that helps you navigate the world. The infrared radiation being emitted by your warm skin carries away excess heat, helping regulate your body temperature. The electrical signals in your nervous system are carrying sensations from your skin, your muscles, your organs to your brain, where they're integrated into your conscious experience. And beneath all of this, at the atomic level, trillions upon trillions of electromagnetic interactions are happening every second, holding molecules together, driving chemical reactions, enabling the metabolic processes that keep you alive. You are not just surrounded by electromagnetic fields, you are made of them. Your very existence depends on them. Without the electromagnetic force, there would be no atoms, no molecules, no chemistry, no biology, no you. The electromagnetic field is not separate from life. It is essential to life. It is what makes complex structure possible, what allows information to be encoded in molecules, what permits energy to be stored and released in controlled ways. Every living thing on Earth is an electromagnetic phenomenon, a pattern of charges and fields organized in specific ways, maintained far from equilibrium by a constant flow of energy. You are a temporary eddy in the great river of electromagnetic interactions that fills the cosmos. A localized increase in complexity and order, sustained by the energy streaming from the sun and the chemical potential stored in the molecules you consume. For a brief time, a few decades if you're fortunate, you persist. You maintain your pattern. You experience and act and change and grow. And then, eventually, the pattern dissolves. The electromagnetic organization that was you returns to simpler forms, and the matter and energy that briefly composed you rejoin the broader flows of nature. But while you're here, while the pattern persists, you are a miracle. You are one of the most complex structures in the known universe, a self-organizing, self-aware electromagnetic system, capable of contemplating its own existence and the nature of the forces that give it being. There's a profound beauty in this realization, a kind of peace that comes from understanding your place in the larger scheme of things. You're not separate from nature, not alien to the physical world, not a ghost piloting a machine. You are nature, a particularly intricate and self-aware part of it, but made from the same stuff, following the same rules, connected by the same forces. The electromagnetic fields that fill the universe also constitute you. The photons that left distant stars millions of years ago, and the photons being emitted by the device you're using to listen to these words right now, are fundamentally the same thing. The electrons flowing through the circuits of that device and the electrons flowing through the neurons of your brain are identical particles, indistinguishable, subject to the same quantum rules. There is no fundamental separation between you and the rest of the cosmos. The boundaries we perceive, the sense that you are here and the world is out there, are useful fictions, convenient ways of organizing experience, but not deep truths about the nature of reality. At the deepest level, everything is fields and particles, energy and information, patterns and processes, all interconnected, all following the same underlying principles. So as we come now to the end of this long exploration, let's rest in this knowledge, not as a cold fact, but as a warm truth. The invisible forces shaping everything are not distant abstractions. They're here, now, in you, around you, connecting you to everything else. You are held, always, by fields that have existed since the beginning of time and will continue to exist long after you're gone. You are part of an ongoing process, a cosmic dance of energy and matter that has been unfolding for billions of years and will continue for billions more. Your individual existence is brief, a flash in the vastness of cosmic time, but it's not meaningless. You are the universe becoming aware of itself, matter organized in such a way that it can ask questions, seek answers, experience wonder. And right now, in this moment, you have the opportunity to appreciate that. To feel gratitude for the improbable gift of consciousness, for the electromagnetic fields that make your awareness possible, for the light that allows you to see, for the bonds that hold your body together, for the signals that carry your thoughts. You are a pattern in the field, and the pattern is beautiful. So let yourself rest now. Let the fields hold you. Feel the weight of your body, supported by electromagnetic forces pushing up from below. Notice the warmth of your skin, infrared radiation gently radiating into the space around you. If there's light, let it enter your eyes without effort, just receiving, just noticing. If it's dark, rest in the darkness, knowing that even in darkness, the electromagnetic field is there, invisible but present, ever present. Thank you for joining me on this gentle exploration of the hidden forces that shape everything. Whether you've stayed awake through this entire journey or drifted off somewhere along the way, I hope you found something here that brings a sense of wonder, a deeper appreciation for the invisible architecture of reality. Remember, you are not separate from the electromagnetic fields we've been discussing. You are part of them, made from them, connected through them to everything else in existence. The light that touches your eyes, the warmth you feel, the thoughts passing through your mind, all of it is electromagnetic. All of it is connected. All of it is part of the same grand pattern that fills the universe from the smallest particle to the largest galaxy. You are home. You've always been home. You are exactly where you belong. A beautiful, temporary, infinitely precious pattern of electromagnetic activity, peacefully existing in this moment. Rest now. Let go. Allow the fields to carry you gently into sleep, into dreams, into the quiet spaces where consciousness softens and dissolves. You've done enough for today. You've learned enough. You've wondered enough. Now it's time to simply be, to exist without effort, to rest in the knowledge that you are held, supported, connected, and loved by the very structure of reality itself. You are an electromagnetic miracle, and you are enough. Close your eyes. Breathe slowly. Feel yourself settling, sinking, softening. The universe is vast, but you are part of it, woven into its fabric, inseparable from its essence. And in this moment, that is all you need to know. Sweet dreams, dear listener. From the Sleepy Library, with gratitude and warmth, good night.